We are speaking all today about capacitors and what they do. So I want to start by talking about the fact that capacitors do store energy, but we haven't really talked about the storage of energy yet. We know that in a parallel plate capacitor, there's going to be an electric field. We know the electric field has a potential difference or is created from a potential difference. And we know that a potential difference is based on the concept of energy. So let's walk with that a little bit and take a look at our definition of I guess the best way to do this would be to say that we know that dW equals QdV for a capacitor. If we're going to charge a capacitor, we're going to change its capacitance. We're going to change its voltage by applying a potential difference to the capacitor. Charges are going to flow in the capacitor, and as the charges flow in the capacitor, they're going to build up charge. In fact, it might be better if we apply a constant voltage to consider the work done might be on the buildup of charge. So since we are not starting with a constant charge, we're actually starting with a constant applied voltage. Let's talk about charging a capacitor by applying a fixed voltage and then waiting to see how much charge builds up on the capacitor. The total amount of work done would be the amount of energy stored in the capacitor. So I think that would be the way that we're going to approach this. How much energy is stored in the capacitor by building up charge on a capacitor with an applied potential difference. Now, that's just as simple as saying, starting with a potential difference, a battery, having a switch in place, have a capacitor, and then maybe a black box here that I'll describe as a charge counter. So right now we start with an uncharged capacitor. We close the switch. That applies a potential difference across the capacitor. And maybe we have a little guy in here who can just count how much charge passes through this little gate so that we know how much charge is moved to charge at the capacitor. If we do that, we should be able to figure out the entire work done in charging the capacitor over, say, I don't know, a few moments as we get it from no charge to full charge. Now, applying a potential difference doesn't mean that the capacitor has a potential difference all at once. We know that in a capacitor, based on the definition of capacitance, that the charge on a capacitor is based on the applied potential difference, but the potential difference isn't there all at once. In fact, we could argue that rearranging this, the one thing that is actually fixed is the capacitance. Meaning, if I put a capacitor in a circuit, the amount of charge on it and the amount of voltage on it vary, but the capacitance doesn't ever change because the capacitor is a fixed object. And its capacitance is based on things like the separation distance between the plates and the area of the plates. Those kinds of things determine what the capacitance is. But if I apply a potential difference, I will move charges. I apply a bigger potential difference, I will move more charges. So maybe if I write this as, I don't know, V equals Q over C, I could do a little bit of a substitution here to talk about what the actual potential difference would be over the capacitor as charges build up. If I do that, I might be able to determine how much energy there is in the capacitor, assuming I charge it from 0 to fully charged. Now, the full charge state will be when my applied potential difference is reflected in the capacitor. What I mean by that is, right now, this represents a transient position within the capacitor. I've built up some charge, and the potential difference across the capacitor is some value, but it's not yet the full value applied by the battery. Eventually, I will get to the full value applied by the battery, where the potential across the capacitor equals the potential of the battery. But you understand that there's a point in the middle when we're charging the capacitor, while we're waiting for charges to be deposited on the capacitor, where the voltage of the capacitor starts at 0 and slowly builds up until it reaches maximum potential difference when it matches the battery. Does that make sense to you guys? That may happen very fast, but it's not instantaneous. It takes a little time for that to occur. So if I close this switch, it's not like suddenly there's a potential difference that matches the battery. What happens is there's an applied potential difference across the plates, and charges are moved, and the voltage starts at 0 and will increase until the voltage across the capacitor each matches the voltage from the battery, the applied voltage. It's not instantaneous. Now, we don't know how long this is going to take. I can tell you that the time that it takes will depend on how much current can flow in the circuit. And I described current already once, but current is the flow of charged particles. So if you have a lot of flow of charged particles in your circuit, you could probably build up that voltage pretty fast. But if you can restrict the flow of those charged particles, it might take longer for you to be able to build up the voltage across your capacitor. Right now, we don't know about any devices that can restrict the flow of charged particles, but they're called resistors. And we're going to be doing circuits that have resistors in them later. We'll talk about how long it might take to charge up a circuit once we have an idea about how resistance works. But right now, we're just talking about the capacitors. We're going to close the switch, charges will flow in the circuit, and the capacitor will start at 0 and then will ramp up until it has the same potential difference as the battery. Does that make sense? It's at that moment that we have a fully charged capacitor, and it has the maximum amount of charge that it's going to have. That maximum amount would be, VA times C, where VA represents the applied potential difference. All good so far? All right, well, the capacitance is the one thing that doesn't change. So if I want to find out how much actual work is done, I just got to do this particular integral, which is not particularly hard. I pull the 1 over C out, and I'll have the integral of Q dQ. And this is going to go from 0 to max charge. Well, can we all agree that the antiderivative of Q is going to be 1/2 Q squared? Because we've kind of done this one before. So this will be 1 over C times 1/2 Q squared, evaluated from 0 to Q. So the work done in charging our capacitor is going to be 1/2 Q squared over C. Does that make sense? Now, this is actually going to be the potential energy stored in a capacitor. The work done in charging it is from an external source. And I know that work is equal to minus the change in potential difference, but the work done from our external source equals the amount of energy stored in the capacitor. So this would be negative the work done by the electric field in the capacitor. But from us, we're the external source pushing charges. So the amount of work we do by pushing those charges is equivalent to the amount of energy stored in the capacitor. Remember, that negative sign that we have in things like this is always about doing work against a conservative force. So if we're tracking the energy, our applied voltage did the work to charge the capacitor. So that applied voltage lost energy so that the capacitor could gain energy. So I don't want to get too tied up in the positive and negative here. The capacitor is charged. It has energy in it now. That is a positive amount of energy. We all good there? Don't get too worked up with that. A thing to think about, though, is it's probably more likely that we are aware of how much the potential difference was that was applied to the capacitor, more so than the amount of charge that flowed to the capacitor. So although we did this by integrating the charge, because we know about how charge is related to capacitance, we can always take this and do some substitution. One of the most likely substitutions that you should do is to consider that just plug in the potential difference in place of the charge. If we do that and do a little bit of algebra, we'll find that we can also write the potential energy as 1/2 C applied voltage squared. This is probably the most useful expression for the potential energy in a capacitor, because it's based on the capacitance and an external value you can read right off the battery, as opposed to having to calculate what the maximum charge in the capacitor is just so you can figure out what the energy is. This will be more direct. So we'll find that there's always a different way to calculate energy in some kind of circuit. So you can probably imagine there's a third way to do this where we get rid of the capacitance and only talk about the charge and the potential if you wanted. So there are three different ways to calculate the potential energy in a capacitor when it's at full charge. This is one of them, this is the other one, and the third one would eliminate capacitance. We just don't use that one very often. Now, help us understand how energy flows and how charge flows in a circuit. But they can be used to solve a circuit. And I'm going to explain what I mean by solving a circuit here in a moment. First, your job is going to be to construct circuits. From this point forward, we're going to be building circuits all the time, which means you have to learn how to read and understand a simple schematic diagram. Now, all circuits have a certain few features in common, and that is a circuit doesn't exist until you have a complete pathway from one side of your potential difference to the other. That's a circuit. Any opening in your circuit means it's not a circuit. So if I start with the potential difference, and your potential difference doesn't have to be a battery. Your potential difference could be a charged capacitor. But either way, there must be a complete conducting pathway through all of your circuit elements that connects one side of your potential difference to the other. That's a circuit. The first circuit I want to talk about is a simple system of capacitors. Because working with one capacitor is no big deal. Working with a system of capacitors begins to help you understand the nature of what I mean when I say solving a circuit. In order to solve a circuit, I'm asking you to figure out the properties of the circuit while it's performing. Now that means different things depending on the circuit elements in your circuit. But ultimately, you should be able to tell me the following things about a circuit. Now, not all of these things may exist in every circuit, but you should be able to tell me the current flowing through any circuit element that supports current. You should be able to tell me the potential difference across any circuit element that has a potential difference. You should be able to tell me the charge stored in any element that can store charge. And you should be able to tell me the energy stored or the energy being dissipated by any circuit element. So current, potential difference, charge, and energy. That's solving a circuit. Now, not all circuit elements will do that. I'll say them all over again. I see three people looking at everybody else's notes. So the charge for any object that stores charge. The current for any object that passes current. The potential difference across any circuit element that has a potential difference. And the energy stored or the energy dissipated. Not all circuit elements store energy. Some circuit elements consume energy, which is why I have to say energy stored or energy dissipated. We just described the fact that capacitors store energy. So we'll be talking about the energy stored in the capacitor. We also just made it pretty clear that capacitors store charge. So in solving a circuit, I expect you can tell me how much charge there is on each capacitor. And lastly, a capacitor operates by having a potential difference. So you should be able to tell me the potential difference across any capacitor. Now what I have here is a very simple circuit. In fact, this has a name. This is called a series circuit. In a series circuit, you have one circuit element connected after another in a single line not to be confused with the parallel circuit, which we'll look at in a few moments. Now, using Kirchhoff's laws, one of the things that we can do is analyze what's happening in a circuit. And here's the first of Kirchhoff's laws. What Kirchhoff what Kirchhoff did with energy is he said, in any closed loop through a circuit, the sum of all the voltage drops has to be equal to 0. I'll say it again. In any closed loop through a circuit, the sum of all the voltage drops has to be equal to 0. Now, the actual activation of this, how you have to use this, is a little bit more difficult than the rule itself, because some things are active voltage supplies, and they add voltage, and some things consume voltage, meaning they require voltage, and they subtract voltage. And it also is directional. So when you're going to apply this rule, what you have to do is identify a loop in your circuit. This one only has one loop, so it's pretty easy to identify. And if it were me, I actually draw an arrow indicating the direction I'm going to proceed through the loop. This part's important because active power supplies can be both positive and negative depending on how you draw your loop. So as you've seen, I've drawn my single loop through the circuit. When you go from the negative side to the positive side of a circuit element, you are increasing the potential. And when you go from the positive side to the negative side of a circuit element, you are decreasing potential. This is important for capacitors, because if you look at the way I've connected this, it might be confusing how things are going to behave, but if you think it through, you can probably figure out where the positive and negative side of each of these circuit elements is. Let's consider that we already know that this is the positive side of the battery and this is the negative side of the battery. We know that already. Now, if you consider the capacitor here, this plate right here, just this one, we're going to be attracting electrons away from it when we close the switch, which is going to make this plate more positive. And of course, we're going to be sending out electrons here at the bottom of the battery because we have a concentration of negative charges there. They will be pushing charges into the capacitor down here. Now, as discussed before, there is no charges passing through a capacitor. But the moment the bottom plate becomes negatively charged, this one right here, it's going to push electrons away from the top plate, which is going to make this capacitor positively charged, or this capacitor plate positively charged, and this capacitive plate negatively charged. This inner piece is disconnected from the circuit, but that doesn't mean we can't influence the charges by induction, which is what's happening here. So now if you take a look at this particular loop, you'll notice that we are going to add potential because we're going from the negative side to the positive side of the battery. Then we'll subtract a potential difference across capacitor 1. And then we'll subtract a potential across capacitor 2. And now we're back to where we started, so this sum has to be equal to 0. That's how you apply Kirchhoff's law to a single loop within your circuit. Kirchhoff's law generates relationships, kind of like Newton's laws. It generates relationships. Those relationships may or may not be useful to you. Our hope is that they will be able to tell us things about our circuit. So, Kirchhoff's first law is a conservation of energy rule. It says that if you have any closed loop within a circuit, the sum of the voltage drops equals 0. We have applied Kirchhoff's rules to this circuit. All good so far? Now, Kirchhoff's second law we can't apply here because Kirchhoff's second law is conservation of charge, and it works when we have a junction in a circuit, a place where the current can go in two different directions. So that's a junction. There's no junction in the circuit. So in this circuit, all the charge that moves has to be the same everywhere in the circuit. Now that brings me to an interesting point, and something that I don't know if you could figure out on your own or not. But you notice I talked about the movement of one charged electron, correct? That was my example, one charged electron. I pulled one electron from this plate, thus it became positively charged. And I pushed one electron to this plate, it became negatively charged. Is it clear by that discussion that there's no way the charge on this capacitor can be different than the charge on that capacitor? Does that make sense? So this is a rule. It's not a law, it's a rule. But capacitors in series will always have the same charge. Capacitors in series will always have the same charge. Okay, I'm going to keep going, all right? Now, one of the things we are hoping for is we're hoping for a situation in which we can solve our circuit. And I indicated that solving a circuit means being able to figure out the potential across each of my capacitors and maybe figure out how much charge there is on each of my capacitors. Right now, all I can tell you is that the charge on each capacitor is going to be equal to Q. I know that's going to be the same amount on both capacitors, but I don't know how much that's going to be. But there is ways for us to consider what it probably would be. Look over here for just a moment. We know what the applied potential difference is to our circuit, V naught. We know that that potential difference is going to be split up amongst the two capacitors. Right? We get that from Kirchhoff's laws. So if I apply 5 volts to my capacitors, whatever my voltage is across one capacitor and the other capacitor will have to sum to be 5 volts. So already I know that the voltage is going to be divided amongst the elements that are in series. That's something that we should expect, that whenever we have elements in a series, capacitors or anything else, elements in a series are always going to divide the voltage. That will always be true. So whenever you have a circuit that has circuit elements in a series, you know that they're going to split up the voltage somehow. So all circuits that have series elements are voltage dividers. In fact, this next part is a little bit tough. We don't have much to work with here, but we have a few things we can work with. And one of them is that we already know something about our circuit. We know that the definition of capacitance is Q over V. Right, we know that. Now we have two different capacitors here, and although we don't know the individual voltages, we could probably start to work this out. In fact, one thing I'd like you to consider is that we could rewrite this, instead of in terms of potential, maybe in terms of the capacitance. Since we know V is going to be Q over C, we could write this as Q over C1 plus Q over C2. Right? We know Q has to be the same for both. Now this gives me pause, and I want you to think about this. The battery doesn't know that there's two capacitors out there. Right? The battery just supplies a potential difference and delivers charge. But the battery probably thinks there's a capacitor out there that has some amount of charge because it knows how much charge it sent out, and probably observes that there's a total capacitance that it thinks might be there. It's not that the battery thinks, it's that the battery can only send out an amount of charge based on the total capacitance of the circuit. It doesn't know that there's 2 capacitors or 100 capacitors or 1 capacitor there. The amount of charge that will be sent out is based on the total capacitance. what this lets us do is come up with an expression for what's called the equivalent capacitance of the circuit. If you have a circuit in series that's made up of nothing but capacitors, then you can calculate what's known as the equivalent capacitance of the circuit. Bringing this up because one of the things I expect you to be able to do is tell me the total charge on each circuit element. This offers a way for us to figure out the total charge on each circuit element by considering what the equivalent capacitance of the circuit is. Let me show you how this might work. In my box over here, I have a variety of capacitors. But right here, this is a 100 microfarad capacitor. And this is a 50 microfarad capacitor. So let's say that I have a circuit.
The first capacitor and the second capacitor are the same, but when we did
Are you saying why didn't I add these two together?
no, on the other side, like why is it like the total capacitance? Why wouldn't it be under 2Q? Like didn't you like add the Q's or something?
Which has a 100 microfarad and a 50 microfarad. And we connect it using our little USB connectors, which provides 5 volts. Can you figure out how much charge there must be on each capacitor with what I just suggested we use? This idea of equivalent capacitance. What we're doing here is something called stepwise reduction. It's one of these ways of getting around using Kirchhoff's laws to do all this work. We're going to use the result of Kirchhoff's laws and apply it in maybe a way that wasn't intended to do what's called stepwise reduction. What we're going to do is we're going to take our circuit and we're going to reduce it to a simpler circuit. One in which we take our 2 capacitors that are in series and replace it with an equivalent capacitance. Reducing a circuit and making it simpler makes it easier to analyze. The fewer circuit elements, the easier you can apply the rules. So I'm going to use this equation to deal with the fact that I have 2 capacitors in series. Now, you have to do some math here. It's not particularly tough, but let's see if you guys can figure it out. I want the equivalent capacitance of these 2 capacitors. Leave your answer in microfarads, so you're not trying to convert it to like 0.000 something or other, okay? So here's how we do it. We'll do 1 over CT equals 1 over 100 plus 1 over 50. We get common denominators of 100, does that make sense? Which will give me 3 over 100. That's not the answer. The answer has to be inverted, so I'll get 100 over 3 as my equivalent capacitance. So 100 over 3 microfarads. Still applying 5 volts, but now it's to an equivalent capacitor. But I know that Q equals CV, right? Taking that definition of capacitance, rearranging it again a different way. This should tell me what the charge is, right? So 100 over 3 times 5. That's 500 thirds, and that would be microcoulombs. We had microfarads before. We're using volts, so that's microcoulombs. That's one of the benefits of using the whole, micro, nano, pico. Go ahead, you have a question.
Yeah. I was wondering on the last why would it not be like 2Q? Like when it was Q over CT equal to Q over C1 plus Q over C2. I know.
So this tells me the charge on my capacitor, but we got this from reducing two capacitors. And we know those two capacitors have to have the same amount of charge on them, which means the charge on this capacitor is 500 thirds microcoulombs, and the charge on this capacitor is 500 thirds microcoulombs. Well, V equals Q over C, right? With that being said, I can divide both of the values of charge by the capacitance, and this should give me the number of volts on each capacitor. So 500 thirds divided by 100 is going to give me 5 thirds volts. And then 500 thirds divided by 50 is going to give me 10 third volts. This is stepwise reduction. If you follow what I did, I found an equivalent capacitance first, use the equivalent capacitance to find the total charge on the capacitors, and then work backwards to find the individual voltage on those capacitors. You guys see what I did? Now, check your work. Does 5 thirds plus 10 thirds equal 5 volts? Do you understand that this method doesn't use all of Kirchhoff's laws, but it uses a portion of Kirchhoff's laws to generate a way to reduce our circuit into something smaller? Go ahead. Sure. How I got the voltage? I use this. And I'll do my math. I'll do the math here. The voltage across that capacitor had to be the total charge, 500 thirds microcoulombs, divided by the capacitance, 100 microfarads. And then I just did arithmetic. 500 divided by 100 gave me 5 thirds. And microcoulombs divided by microfarad has got to be volts. Think you guys can do this? Step 1, reduce your system to a single capacitance. Okay, step 1, reduce your circuit to a single capacitance. I have 3 capacitors in series, so I don't think I have to explain this to you, that this is just going to be 1 over 100 plus 1 over 100 plus 1 over 50. Do you guys see that that would just be an additional capacitor and we would just continue the same way? They're all going to have the same charge. Common denominators of 100, and that gives me 4 over 100. So the equivalent capacitance is 25 microfarads. We good there? So my simplified circuit has one capacitor, and it is 25 microfarads. Now I still have my same 5-volt power supply. So I want to find the charge, and charge is equal to capacitance times voltage. So 5 times 25 is 125 microcoulombs. Now this part, stepping back to your previous circuit, we are going back to a system that's in series. I'm going to be very clear about this. Series capacitors have the same charge. So when we step back to a group that's in series, we apply the charge to all the capacitors in series. Because we're going to have parallel circuits here soon. Well, tomorrow. So I reduce the circuit first, then I step back to the circuit with my new information. Now we solve for whatever's missing. We're missing voltage. So because we're missing voltage, we will solve for what's missing by taking the charge and dividing by the capacitance. Then check your work. Does the sum of the voltage drops equal the applied voltage? So is 1.25 plus 1.25 plus 2.5 equal 5?